In this video, we're going to talk about the matrix exponential. And it's a way of exponentiating a matrix. So we know that if you have e to the x, this has a power series expansion 1 plus x squared over 2 factorial plus x cubed over 3 factorial and so on. And this can be written as a sum from n equals 0 to infinity of x to the n over n factorial. And motivated by this definition, we can define e to a matrix. So e to a matrix A is defined to be, so A is an n by n matrix. So A is a n by n matrix. So e to the A is defined to be the n by n identity matrix plus a squared over 2 factorial plus a cubed over 3 factorial plus dot dot dot. Okay. And things like this show up in differential equations, and we'll see that in future videos. But before that, let's just remind ourselves of what this expression even means. So here I is the n by n identity matrix, so it's an n by n matrix. A squared over 2 factorial, a squared is an n by n matrix, and this divided by 2 factorial means you divide each entry by 2 factorial. 2 factorial is 2. So you divide each entry by 2. That's also an n by n matrix. And similarly, a cubed over 3 factorial, 3 factorial is 6. Calculate a cubed, that's an n by n matrix, and then you divide each entry by 6, so that's an n by n matrix. So you're summing a bunch of n by n matrices, and the result is an n by n matrix. So this e to the a is an n by n matrix. For the purpose of this video, by the way, since this is an infinite series, there's this potential issue where you might get infinity. Okay, but in this video, let's just not worry about that and assume that for the a's that we're going to be working with, you won't have this issue of the series diverging, right, to infinity. Okay, let's just look at some examples. So actually, we will also look at e to the at. This one is the one that we will really consider. Now, this is if we have an n by n matrix A and then multiply each entry by t. So AT is a n by n matrix. It's just that instead of numbers, it's going to have t's in it also. So this is going to be the n by n identity matrix plus AT squared over 2 factorial plus AT cubed over 3 factorial, etc. And then you can just distribute the t across, so it's going to be in plus a squared t squared over 2 factorial plus a cubed t cubed over 3 factorial, and so on. And so, yeah, so you just take your a squared, so for this a squared t squared over 2 factorial, you would take a squared and then multiply each entry in the matrix by t squared over 2. And similarly, for a cubed t cubed over 3 factorial, you take a cubed and then multiply each entry by t cubed over 3 factorial. So t cubed over 6, and so on. So here are the main examples to keep in mind that are relevant for differential equations. So you can just do e to the at just for any matrix, as long as the series converges. But there are a few examples that are particularly important. So one of them is when A is a diagonal matrix. So let's just look at a simple example. Suppose that A is this matrix, say A, B, C. So it's a diagonal matrix. Okay? So let's just call it A, D. So D equals A. D is the name for this matrix. So we're calculating e to the at, that's e to the dt, okay? So we need to know the powers of this matrix. Well, we know that since you have a diagonal matrix, this is just going to be d to the n is just a diagonal matrix with entries a to the n, b to the n, and c to the n on the diagonal, right? So e to the dt is going to be I sub n plus d squared t squared over 2 plus d cubed t cubed over 3 factorial, so I'm just going to write factorials, plus and so on. So what is, well, the n by n identity matrix is just this, okay? What's d squared t squared over 2 look like? Well, that's going to be a squared times t squared over 2, and then b squared t squared over 2, and then c squared t squared over 2 on the diagonal. And what is d cubed t cubed over 3 factorial going to look like? Well, that matrix is going to look like a cubed t cubed over 3 factorial, b cubed t cubed over 3 factorial, c cubed t cubed over 3 factorial on the main diagonal. And you just keep going, right? So now when you add these matrices and you go on forever, what you're going to get, this top left matrix in the 1, 1 entry is going to be 1 plus, let's factor out the a squared t squared, so it's going to be at parentheses squared over 2 factorial plus at cubed over 3 factorial plus dot dot dot. That's going to be the top left entry, and then you get 0, 0. And then you're going to, in the second row, you're going to get 0 here, and then in the 2, 2 entry, you're just going to get the same thing except with b's. So it's going to be 1 plus bt oh, wow, I completely forgot the a. So it's at. Sorry. So I have a dt here. So dt is going to be at, bt, ct. Okay, so I have this at plus here. So now I have this 2, 2 entry. I'm going to have 1 plus bt plus bt squared over 2 factorial plus dot, dot, dot. And then similarly, in the 3, 3 entry, I'm going to have 1 plus ct plus ct squared over 2 factorial plus dot, dot, dot. So what is that? Well, the diagonal entries are just e to the at, e to the bt, and e to the ct. So in general, if D is a diagonal matrix, say with entries lambda 1 to lambda n, then e to the dt is just a diagonal matrix with entries e to the lambda 1t to e to the lambda nt. So that's the first main example. Okay. Okay. So that's the first main example. Then, so when you have a diagonal matrix, it's really easy to do e to the dt. Let's look at two more examples. So one of them is if A is this 2 by 2 matrix, 0, 1 on the first row and 0, 0 on the second row. So to calculate e to the at, we need the powers of A. So if you take A and then multiply it by itself, A squared is A times A, and I'll let you check that you just get the 0 matrix. So 0, 0, 0, 0. Now if that's A squared, what's A cubed going to be? Well, A cubed is A squared times A. So if A squared is the matrix of all zeros, then that times A is also going to be the matrix of all zeros. And so on. So basically you have A, but then A squared, A cubed, A to the 4th power, and so on are all the 0 matrix. So that's actually going to simplify this matrix exponential, because remember e to the at So I'm calculating e to the at, not just e to the a, in these examples. It's I plus a, why do I keep skipping the a term? I plus at plus a squared t squared over 2 factorial plus a cubed t cubed over 3 factorial, etc. But a squared and a cubed, etc. in this example are all 0. So, right, they're all the 0 matrix, so all these are going to be the 0 matrix. Right? These are the 0 matrix. So you really just need to calculate I plus AT. Well, that's easy, because I is just a 2 by 2 identity matrix. AT, so I take A and then multiply each entry by T, so I get 0, T, 0, 0, and then I add them. So I get 1, T, 0, 1. So that's my matrix e to the AT. Let's do one more example, which is like a 3 by 3 case of the one we had before. So let's say that A is this matrix 0, 1, 0 for the first row, second row 0, 0, 1, third row 0, 0, 0. So I'll let you check that A squared is the matrix whose first row is 0, 0, 1, and then the other rows are 0. And A cubed is going to be the 0 matrix. And once you get A cubed to the 0 matrix, of course, all the other powers, A to the 4th, A to the 5th, etc., are all 0. So now e to the AT is going to be I plus AT plus A squared T squared over 2 factorial. Because A cubed and A to the 4th, all those terms are going to be the 0 matrix. So they're not going to affect the sum. All right, so the I matrix is going to be the 3 by 3 identity matrix. AT is going to be 0, T, 0, 0, 0, T, 0, 0, 0. And then the A squared T squared over 2 is just going to be 0, 0, T squared over 2, 0, 0, 0, 0, 0, 0. So the final matrix is going to be 1, T, T squared over 2, 0, 0, T, 0, nope, 0, 1, T, 0, 0, 1. And if you're familiar with second order differential equations with repeated roots, you know that there's like a t squared e to the t in there, right? Or a t e to the t, or t e to the, whatever, t e to the rt, right? Or t squared e to the rt. And that, you can kind of see how that might show up in this matrix exponential, that when you have this 2 by 2 case, you have a t, right? And that t in the e to the at will show up when we look at a 2 by 2 situation with a repeated root in the characteristic polynomial. That this t in the top right is going to play a role. And it's going to explain where you get the t e to the rt from.